Good. Still morning, sorry.
Yeah.
Still morning. India. Today is very hot here in Melbourne, It's almost 36 degrees,
Yeah. Here also the same. The temperatures are quite
Oh. All right. So let's continue.
Yeah. I welcome you back for the lecture 7 on day 3 on the GAN course. Can go ahead, Professor. Can go ahead.
Yes, sure. All right. And then full screen. Okay. This looks fine now.
Yeah. Go to the presentation. Display settings, Professor.
Okay, presentation. Okay, how about now? Okay.
Yeah, it's fine.
Good. Okay, so we back to just to recap back. So we have these types of load, 5 light bulbs of 100 watts and 2 hours a day. And then this fan, for example, and then we calculate the panel. So we add another 30% of losses, so to account for additional load. And then we assume location. We have 6. I think we have explained this very clearly now. Difference between sunshine and sun hours. Okay. So and then we calculate the number of panels. So we got 2 number of panels that is required for this load. And then now the fourth steps is to calculate the battery capacity. Okay. So we want to calculate the battery capacity. What will be the battery required? Okay, the capacity is expected in terms of current. Okay, for particular voltage. Okay, the voltage we can manage it in series. So, for example, we operate at 48 volts. So if we have a battery of 12 volts, so we need 4 of them. Okay. If we operate at 24 volts, so we need 2 of them in series. But what we are interested in calculating the number of parallel, the AH. So, okay, it's called the total watt hour per day for the appliance types, the number of autonomy. Yeah, this is very important. The DA, days of autonomy. Days of autonomy means there is no enough sun to charge the batteries. Means the load will only depend on the battery. That's the number of autonomy days. Okay, and then if we assume that the batteries is 85% efficiency, so divide by 0.85 depth of discharge. Okay, times the nominal voltage battery. Okay, and then the rule of thumb: the battery voltage must match the voltage of the panel. So let's calculate this. So the total watt hour per day. So we assume 3. Okay, divide by 0.85, divide by 0.6, multiplied by 24, which is the battery for. So we get the AH, which is almost 510 AH. So that's the size of the battery. So AH divided by 150 AH per battery, so it gives you 3.4. So we can get around 4 batteries. Okay, so this is to calculate the size of the batteries. All right, then now step number 5, the inverter capacity. Okay, so if we're having a load, okay, so if we assume both of them are AC loads, so we have 500, and then we have 360, so we have a total of 860 watt. Okay, all right, and then yeah, this is what just now we asked. I remember the one inverter, the capacity. So we capacity, it's 0.860 divided by 0.7, which is the inverter efficiency. Okay, all right. But if we assume the inverter efficiency is 1, then it will be 1.2 watt, which is 1.2 kVA. Okay, but don't worry about this one. We will come to it later. So the inverter sizing. So we get the inverter size. Okay, the number of panels. Okay, charge controllers, because we need the charge controllers because we have a battery. So the AH, the short circuit current, which is around 9 amperes. So the number of panels, like we said just now, we have 2 panels multiplied by 1.3. 1.3 is the safety margin. Okay, so safety margin, or we call it the safety factor. Okay, so the number of panels multiplied by the short circuit current multiplied by 1.3, which is the safety. Means we increase in case, for example, there is a shoot of the current. Okay, all right. I know there will be some questions, so we will discuss it after this. Okay, so we calculate the charge controller ratings for the current. So the charge controller capacity is a number of modules times the short circuit current times 1.3 to accumulate for things. So we have 2 panels times the short circuit current times 1.3, so it is 23. So the charge controller must have a capacity of between 25 to 30 amperes at 24 volts. So we know the inverter, we know the charge controllers, we know the battery, we know the PV panel. So now it's ready to design the system. Okay, any questions for this example?
Professor, this charge controller,
Yes.
it have a transducer, right?
Sorry?
Is it going to have a transducer in the charge controller, or
It has what? Transistor?
no, transducer? See, you have
Yes. Oh yeah, yes, for sure it has. Because it works on sensing the voltage and current on the battery. Because
but this charge controller don't have the capacity of 23.27, right?
sorry?
Is it required to have the rating of the charge controller?
Yeah, because the different charge controllers, you have a different number of batteries and different number of panels. For example, you are using 10 panels. Okay, so to connect, you need the different charge controllers. Yeah, because different sizes. If we have 1 panel, 2 panels, because the charge controllers depends on the number of panels. Because that is connected to the panels to the battery, right?
Okay.
That's how it charges. Otherwise, how is going to charge the batteries? Okay. Any other questions? Okay. If there is no questions, let me go back to the inverter. This is very I call it rough calculations. It's a very where is the how to stop and show this card. Okay, and show, and then stop sharing. Okay, let me share with you something. Just now I talk about the inverter. Okay, gain. By the way, have any questions? Any questions on this? Is there any questions that I'm just looking for the grid connected PV systems design. Yeah, is the one. Yeah. Mr. Siva, any questions in the chat? No. Okay. No worries. Okay. So what I have shown just now, it's a very rough estimation. It's a very simple calculations. Okay. But if we want to do a very detailed and we call accurate calculations, then I will share with you this. Let me. All right, presentation, share, present, entire screen, screen number 2, share. And then put on slideshow. Okay, and then.
Yeah, it is fine, Professor. It is fine.
Huh?
Yeah, it is fine.
It's okay?
Yeah, it's okay.
Okay, good. That's good. Okay, let me take the pen. All right, that pen. Okay, so let me. I think we have seen all this. Okay, I think grid connected, and on grid this is the control of grid connected and the control. Okay, so basic. I think we have explained this. So there are a lot of factors that actually when we calculate. For this is what you call a detail calculations. It's not like just now we did a rough estimation. We didn't consider the location. Did we consider the location just now? No. Did we consider the tilted angle? No. Did we consider the orientation? No. We didn't consider anything. It's just like a rough, we call it a rough estimation. It may not be accurate. It may not be what you call details. But actually, if we want to do a design grid-connected PV systems, especially for the microgrids, there is a very detailed and precise methods and way on how to calculate it. First one, okay, as I think we know, the Earth is rotating, all right, around it. I think have two rotations, right? It's rotating around itself, and it's rotating around the sun. There are two rotations. Okay, it's rotating around the sun and it rotates around itself, and it's rotating with an angle. We call it the axial tilt. Okay, and this angle is around 23.45. Okay, so I think we know the rotations of the Earth around the sun, creating the seasons. And the rotation spins on its axis create the days and nights. Okay, I think all of us knows this, So that's the total number of days and then things. Okay, I think that's very good. So if you look into this, you can see actually the Earth, how it is located, So different zones, okay, and the calculations, the degrees, how we convert from degrees to what I call kilometers, from minutes to kilometers, and then from seconds to meters. So the equators usually is referred as 0. Okay, the tropic Cancer is 23 degree north. The Arctic circles is around 66.57 north, and so on, and the south is the same things. Okay, but this is not my so this is, I think, two details. Let me show you. Okay, actually, when we want to do the calculation of or we want to size the PV systems, we always start with what we call solar time. Okay, we call it ST, solar time. So everything has to be converted to solar time. Because, for example, you are in India, you use the Indian Standard Time. You are in Australia, we use the Australian Standard Time. In America, they have this. So they have different time zones, which we know how these time zones are being created. Okay. But when doing the calculation for solar, we use a different time. We call it the ST, which is the solar times. And this local solar time, is the position of the sun at a particular site. That's what we care. We don't care about what is the time at the time. And then we have what we call the local time, which is the official time of the region, okay, by which we use by local clocks. Okay, for example, 12 noon LST, which is a local solar time, is a solar noon, is when the sun is right, the highest in the sky. So this is the definition of the LST. Okay, and then we have the LSTM and so on. And this is given by this equation. We use this equation actually. Okay, the LST equal to LT plus K plus L site minus LSTM plus the equation of time. So K is a conversion factor, okay, which is 4 degrees per minute, okay, and the LST is the longitude of the site and the equation of time. So when we want to calculate the local solar time, we always use this equation, okay. And this is the LST, for example. You know, we have LST for certain location. For example, we have longitude of site, which is 110 degrees east. And if this longitude of is around 120 degrees, calculate the local solar time when the local time is 3 p.m. on 1st of March. You see? 3 p.m. on the 1st of March, the specific date. So we come here, we calculate, okay, LST, okay, is equal to 3 p.m., which is the LT, okay, local time, plus the K, which is the 4 degrees, the factor, 110 minus 120 plus 12 minus 12 minutes, okay? So we calculate, and this 12 minutes is the equation of time. Huh? This equation of time, if you come here, and then you can calculate. So we're having, this is the curve of the equation of time. So it's in the 1st of March. This is the 1st of March. And then you come here, it is equal to minus 12. So for example, if you're having 1st of November, then this is the equation of time. And there is the formula actually how to do it. So the curve of time is around maybe 16 or 17. All right. So actually, the local solar time is 14:08 or 2:08 p.m. So actually, it's not 3 p.m., but it is 2:08 p.m. Okay. So this is how we calculate the local solar time. Okay. And then we have the I think we have, I mentioned this before, the solar path, which is actually the altitude, okay, and the azimuth. I think we have explained, and then we also talk about the beta, the tilted angle, okay. And this is what you call the sun path, which we use this sun path to see the movement of the sun. You know how the movement of the sun at different locations. For example, this is in the location in Kuching on 23rd of November 2018. This is how the path of the sun moves for every location, okay. And then we come to what you call to the tilt angle beta, okay. So what is the maximum or the allowable beta? Like we said before, we use either 15 or degrees, but that's the rough estimations. But actually, this is how we should calculate, you know. Okay, the theta, okay. Okay, for example, determine the solar altitude, okay, for the angle. So this is the calculations. It's very detailed, but I'm not. So this is another example, okay. And these are the definitions. I think many people confuse what's the difference between solar irradiance and solar irradiation. You know, solar irradiance is watt per meter square. Solar irradiation is watt per meter square. We use H and G. You know, so this is, be careful. Solar constants, usually we use it, it's under the reference, which is around 1,367 watt per meter square, which is at the atmosphere. And then we have the peak value, which is already we use meter per square to calculate it. So these are some definitions which we use. I think I have explained this before. The difference between the solar I call radiations and the day, you know. So this is the day, you know, you have the day from here to here, but actually what we use only these parts of solar power, okay. And this is what we call the world have what we call solar map. And this solar map actually gives you the things. For example, if you look into India, you see India has a very good access in terms, especially southern India, very good solar. And I think this is Tamil Nadu, and so this is a very good solar access. This is because Australia also very, very good solar access. This is, I think I mentioned before, the solar pathfinder we use. I think this is how it looks like. I think I have shown this, but this is not. This is how the month and the H for each location. All right, I think we have explained this from cell to module to string and to string in PV modules. I think we have explained this. PV cells we already explained yesterday. This is more details. Okay. Okay, the MPPT or the field, or I call it the field factor. I think this is also important. The field factor is very important to calculate the field factor, which is actually the IMP times VMP divided by short circuit current times open circuit voltage, and this is the thing. So the maximum I call field factor. For example, if you have VOC 35, VMP 26. And then we can calculate the field factor. Field factor is equal to this, is equal to 0.7. So what does this mean? It means the maximum power you can extract from this, it's around 70% maximum. Okay. All right. I think I mentioned about the STC. I think I've explained, but this is the standards. Okay. When we see all this data that we receive, okay, it's always follow the standard, the STC, which is 1000 watt per meter square, 25 degree, and this is AM. AM is the air mass, which is 1.5. Okay. Okay. All right. So I think this is I explained before the data sheet. So we need to know how to read data sheet. This is not this is the data. So the temperature coefficient, very important, thermal. All right, the rating, I think I have explained this one, this data sheet also. Let me go back. Yeah, I think we have explained this MPPT already. Okay. This is what you call the derating factors, which actually take me to the design actually for the inverter sizing and so on. So what are the derating factors due to the temperature? So we have a derating factor due to temperature. As we said before, the cell's temperature is much higher than the ambient temperature. Okay. For example, see, the cell's temperature is equal to the ambient temperature, which is, for example, 20 or 25, like today in Melbourne is around 36. So it's 36 plus this quantity. Okay. So most of the time, the cell's temperature actually, maybe it's around, maybe if it is 25 here, maybe it's around 50 to 70 degrees Celsius. And that's what reduces the efficiency of the cells, because like I said just now, the STC is at 25 degrees C. So when you put it outside, it's different environment conditions, All right. So that's why we call it derating the irradiance. Okay. So these are the estimation of what you call, for example, power at the at different temperatures. So, for example, you see always the power at the thing, then equal power STC, which is as the standard conditions, plus the K, So this is the derating factor. Everyone have a derating factor, You see, even the current also. So you don't get the IC short circuit current. You always have a derating factor, See, even the voltage, we have what you call the derating factor, So we have always a derating factor in all this. Okay. So this is just an example. Okay. So the irradiance is around 600 watt per meter square, ambient temperature of 32 degrees. Okay. The derating factor due to the dirts accumulated on the new PV modules is around 2%. So what does it mean? It means actually we have to derate, okay, due to the dirt. So when we do the calculations, you see, we have the total power is the power at STC, like we said just now, 250 watts, plus derating factor, plus derating factor due to the temperature, plus derating factor due to the irradiance, derating factor due to the dirt, derating factor due to the age. You see how many derating factors? Okay, for this example, for example, okay, so this is an S and P we assume is 1. Okay, so for example, if we have a PV panel of a 200 watt and the STC, you know, actually the power that we get is only 99, 100 watt, half of what we get. And that's why I think I mentioned just now the sizing of the inverter. We never use what you call the WP or the watt peak, okay, because that actually happens at the STC. So the actual, if you calculate all the derating, actually most of the time, if a 200 watts, actually more in the best case scenario, maybe you can get a bit higher if it's not dirty, the area is not dirty, it's clean, and the temperature is low. Maybe you can get 150 watts, for example, as the best case scenario. But this is what's actually happened. Okay, so this is what the things, and even the short circuit current, for example, you see the short circuit current is 6.3. Okay, yeah, here the short circuit current is 6.3, but after we multiply by all the derating, so actually we get only 3.7. The same thing goes for the voltage. So the voltage here, the voltage at STC, it's around 44, I think. Yeah, 44 volts. So, but when we apply the deratings, actually it's becoming 40 volts. So this actually shows the impact of all, because this will never be mentioned anywhere. Just now when we do the simple example, the calculations, we never calculate this, right? We never apply all these derating factors. But these derating factors it's real, you know, it's there, you know, because due to the temperature it's there, due to the dirts. Sorry. Yeah. So different factors have to be taken in consideration. So these are different derating factors due to the module mismatch, power mismatch, because what's the assumption when we put two modules together? The assumption that they are actually 100% the same, right? But actually not. In reality, it's not. You may have one module, maybe the open circuit voltage is maybe 5.6, another one is 5.3. You know, there is 0.3 difference. See, this is what's called derating due to the mismatch. Derating due to this is due to the what you call power mismatch. Also, there is the current mismatch. Derating due to the voltage mismatch. Derating due to the temperature, dirt. Derating due to the irradiance. Okay, the age. Okay, means if I'm calculating for maybe after 2 years, 3 years, 4 years, you know, and so on. And the efficiency, for example, cables. Most of the cable, there are some losses. For example, 3% losses, you know. And number of connections in series and parallel, but if we assume 1-to-1, then yeah. Okay. Any questions here? Because I think this is very important. This is actually the real calculation. But what I showed you just now, it's what I call we call it street, what you call it, ruler. It's a pencil and paper, you know, calculation. But this is actually what have to be, you know, calculated. in order for you to get an accurate PV system design sizing. Okay. Then I think there is one. Any questions so far? Please feel free to ask any questions. If you have any questions. Yesterday, I think there is one question. We on the bypass diodes, on these diodes. Okay. I think, but this picture actually shows an ideal case. So we don't have one panel, one diode. This what you call diodes. We call them bypass diodes. Okay, it's called bypass diodes. Okay, bypass diodes is a PV module, is a string, is faulty, then it will behave like an open circuit. Okay, so it passes the current here, so it passes this module. Because if we don't have this, what happened? The whole this string will be blocked because they are connected in series. Okay, but as I said, okay, so this is the blocking diode. So to block the current going back to the panels for protection. Okay, but this is what happened actually. So when we're having a series connected cells, which is in a single module, what happened? One is shaded. So what happened? This car in the normal one, this is becoming a generator. But if it is shaded, then becoming a load. You can see, all right, becoming a load. So instead of that, then this diode, this current, this voltage here will be higher than this, and then this will be activated, and the current will continue. So we bypass it. So we lost one cell, but we still have maybe power produced, but maybe less compared to. But if we don't have these diodes, what we get here is zero. Okay, plus the damage of this cell, because this cell will be damaged if it is not, because it will be the current will be dropped on this, and it will be damaged with the time. Okay, so this is actually how the connections, I think all of you knows, series connections, parallel connections. So for example, here you're having 3 amp 15 volts. So you have here a 15 volt 9 amp connections. This is the load parallel load connection. I think all of you knows. So this is what you call mismatch, what I mentioned before. Okay, so if you have one panel, for example here, all the panels are 152 volts, 152 volt, 1980 amp, 19.8 amp, 19.8 amp, but this is 17.8 amp. There is a voltage drop. So the total voltage actually is 3 times 19, you get the total voltage. But the total current is 8, because all of them are 8, right? But the total power is this multiplied by 10. Okay? So we have a 16 watt power lower, which is installed. This is what you call a mismatch condition. So this is what happened in the mismatch. So you can see all of them supposed to be the same, but actually there is a mismatch. One of the panels actually producing, because these are, the devices, there is always tolerance. Yeah, 19 volt, maybe one is 18, one is 20, 19, 17. So these are, it's expected in the fabrication. That's why even in data sheets, they will tell you always this plus minus 2%. I think there is one slide I think I show you here. There is always a percentage. You see, plus minus 2%. You see, always the manufacturer, they protect themselves with this by 2 plus 2%. So this is to protect actually themselves, because yes, it's 10, it's 19 volt, but plus minus 2 volt, plus minus 2%. So if you see plus minus 2%, if we see 1%, actually you're talking about 2 volts, okay. Oh, sorry, less, 0.2 volts. Okay. So this is the effect, when we're having a mismatch, panel mismatch. And the same things, when we're having panels, connect them in series and parallel. This is actually straightforward. Okay, let's look into the grid connected, which is actually the control of this. Okay, I think this is one of the participant asked me actually, where is the MPPT just now? So actually, this is how the MPPT looks like. So they have the PV panels, you have an MPPT here, which is DC-DC converters, and then we have the inverter, and then sometimes we have DC loads, which can connect here, and then we have AC loads, and then the grid, which is connected. Okay. Okay, this is a thing that's I think we have talked about this yesterday, which is microinverter, string, central, multi-string, and then transformer without transformerless. I think we have done this before. These are some of the, you know, what you call characteristics of the inverter data sheet. Very important to understand this. Always, because the inverter is an input, DC input. I think all of us knows the inverter supplies an input, DC. So you need to know the maximum power, maximum input voltage, MPPT voltage range, maximum input current, and number of MPPs. Sometimes you have multiple one. You know, the output. What is the rated AC power, maximum power, frequency, and the maximum efficiency? Maximum, you know, means it's not constant. Efficiency is not constant. All right. And then the protection, we have different types of protection that can be used. Yeah, this is a data sheet of an inverter. I think this is so you can see here 16 kilowatt. The voltage, you see, this is what I mentioned just now. The range, the operating range. So this inverter works between 200 volts DC to 500 volts DC. Okay. See, maximum input current 3 times what you call 26 amp. Number of MPP. So this has 3 MPP. So you can connect three panels. You know, 3 strings maybe to this. You know, see. So this is another one. See the output. Sorry, the output is. Sorry, excuse me. It's 13.5 kilowatt. See the efficiency, maximum efficiency. And then we have the European efficiency. Anyone knows what this means, or European efficiency? Anyone knows what is the? You always have this maximum efficiency, and then efficiency. I think all of us knows efficiency is the output power over the input power, right? That's how we calculate the efficiency, the output over the input. But this is maximum, okay? But European efficiency, most of the time, European efficiency is always lower than the maximum efficiency. Why? Because European efficiency, they calculate based not the inverter will not always work at the maximum power. They will work as maybe 50%, 75%. So they calculate that efficiency. So the total will be less always. So if you ask me, the more realistic actually is the European efficiency is more realistic compared to the maximum, because maximum it's at one point, but this is considered the operating conditions of the inverter. Yeah. So this DC, you see, these are data sheet. I think all of you should be able to what you call to read this. You know, very very important to understand. For example, here this is an 8.2 kilowatt systems, maximum input voltage 1000. So this is the operating range. Means this inverter will never work if the voltage is below 320, and we never work if the voltage above what you call 800 volts. Okay, but here maximum, this is for protection, you can see, but the optimum one is around 600 volts. Okay, all right. I think the others, you know, so different. This is the power and so on. So it's all Okay, I think quite important when in the PV system design. I don't know what's the time. Maybe can have some questions because we have discussed quite stop sharing. Slideshow. Discard. Okay, any questions so far? Because I think we have more than 30 minutes. Any questions of this part?
There's a questions in the chat box.
Yeah. Oh, sorry, I didn't see that. Sir, you told transducers are used in charge controllers. Can you please specify? I think we have explained this before. What is this? I don't know. What is ingress current?
I think in ingress, he's writing ingress, maybe a spelling mistake.
I think maybe it's a rush protection, you know.
Yeah.
Oh, what? I don't know. Which slides? Yeah, usually for protections we have protections due to the rush current, you know. So we have some protections, you know. But I don't know which slides actually referring. If it's good, if you can remember. Okay, this guru, you know, if you can unmute and ask us. Maybe there is other questions. Any other questions?
Sir, the bypass and the blocking diodes, is it will be at the cell level or the solar panel level?
The bypass diodes, usually in one panel, usually there are around 36 cells. So they put around maybe 8 cells or 9 cells, one bypass diode. Few cells in series, one bypass diode. Few cells in series, one bypass diode. This is all inside in the panel. If you open the panel from the back, actually you can see the diodes. In the box of the panel, you can see some of them, they have 4 diodes, 2 diodes, you know. So actually, because the panel is in series, the cells are connected in series within the panel. Okay? So they will group few cells and put one bypass diode. But the blocking diode is outside the panel. Okay, yeah. Okay, any other questions? Okay, it's no, so we can continue then. Please put on the if you have any things that you just put on the chat box, and please also unmute in case you have questions. Okay, let me put the slide again. Okay, entire screen number 2, share. Yeah. Okay, it's coming. And then put on slideshow mode. Can you see?
It's not in the slideshow mode.
It's coming. Yeah. How about now?
Yeah, it is fine. It's fine.
Okay, good. Thank you. Okay, so I think very important also in the PV system design, many people actually make these mistakes. They use the same cables in the AC side on DC side, especially if you have grid connected inverters. Grid connected inverters, you have 2 parts. You have the DC side, which is a PV DC-DC converters inverter. That is a DC. And then we have the AC side. The AC side is you use AC cables. Because, you know, wire sizing selections is, you know, very important, you know. Because if you use the wrong wires, you have losses inside these wires. So make sure in the design you use these cables. You can see here, it's written solar cables. This is DC cables. So they are differently designed. Okay. So they have UV resistance. They have, you know, they are double. You can see here double insulations. You know, they have double insulations. You know, the voltage drop is less, you know, due to the resistance of the wire. So this is very, very important. The the selection of the cable. So if you design a PV systems, you remember that we have a DC side and we have the AC side, especially for grid connected PV inverters. Okay. The same goes to protection, current we call current string protections. So usually we see here solar PV. Okay, so these are designed for DC circuit breakers, DC fuses or DC circuit breakers. So this is very important. You cannot just simply use any AC circuit breakers. Very, very important. Because DC circuit breakers, they have the positive and negative. Remember. Okay. And also on the other hand, which is after the inverter, then we use the AC switches. So this is actually very important. Usually double pole or single pole or three phase or whatever, 4-pole, 3-phase. So these are also very important. Also, we due to the lighting, we use the surge protection devices. Okay, so that's actually very, very important. Okay, for protections. If you look into here also for the design, the grounding is very important. The connection, the grounding. You see, we need to have a proper groundings of our panels. Okay, especially all the frames should be grounded using 10 mm copper cables. Okay, so very, very important. This is for what we call protections. Okay. Now we look into the design and the architecture. So I think we talk about it. The architecture real constraints. What does mean architectural constraints? It means sometimes for example, you want to put it on the rooftop. So on the rooftop, you have a limited space. You have a limited space. You have sometimes you have big roof, but not good solar access. So you have a limited. So this is the architectural, size. So you have the PV panel, and that's why comes the selection. What types of PV panels that we should select? Okay, because you may find 1 meter square give you 200 watt, and then you may have another 1 meter square give you 500 watts. If you have a space limitation, so you should go for the 500 watt. Yes, it is expensive. Maybe the price is double, maybe more. Okay, but this is necessary. So that's why you need to. This is to select the right size. For example, if you have like the length of the roof, and the width of the roof, and then you select what is the right size of the panel, because you actually in the market there are many types of panels, many sizes, which gives different power ratings. And this is what we call lengthwise, so the area across. Okay, so you can the roof. I think this is quite simple. I don't want to waste a lot of time in this. This is the width. So this is to get the number of modules. So the lengthwise and length cross up and the cross. So we calculate the number of modules. So for example, we have an area which is 30 meters length, 15 meters width. Okay, using the PV modules of having 1,400 mm length, which is around 1.4 meters, and the width of 0.89 meters. Determine the arrangement that can accommodate the maximum number of modules. If the inter-module gap, because there is always a gap. You see this delta here? This is the gap. Okay, so because you cannot calculate exactly, because there will be a gap of maybe here it is around 0.1 cm. Okay. Oh, sorry, it's 1 cm. That's 0.1. Okay. So energy constraints. Okay. So I think as I see here, it's more detailed. you know. So the amount of energy to be supplied is always given by this equation. Okay, energy required per annum in kilowatt hour. So the percentage of energy supplied by the PV, how much? You want 100%? You want a 50%, 30%, 70%, whatever? Okay, N is the number of, here 12 months, number of months with available data. M is month with available data. Okay, and then energy consumption for 1 month. So that's how we calculate. So design, okay, the minimum number, the minimum power requirement, as I say, it's a very detailed. I don't think so we will have enough time to go through all this, but these slides I will share with you so you can make use of this. So this is the calculations, you know. So to get the power from the array at STC, okay, so it is the energy required, the PSH, which is the peak sun hours, you know, okay, on a plane. The key, which is the derating factor, and then the NS, which is the number of, we call the efficiency of the subsystem, the efficiency of the subsystems. So this is the derating. This one here actually includes a number of derating factors, which is the P, the village power due to the dirts, and then the derating factor due to temperature. You know, you calculate all of this. The submole efficiency, you know, you have the inverter efficiency, and then the cable efficiency. You know, see the inverter efficiency and the cable efficiency, and then the cells. You know, so you get this. So this is the number of modules you round up. Let me give you an idea. This is an example, just to tell you actually how much the effect. You see here, assume provided that 80% of power is provided by PV panels, dirts maybe 4% losses. The temperature is around 36 degrees. We have 5 sun hours a day. Losses in the cable, the efficiency is 97.5, so there is around 2.5 losses. Inverter efficiency 97, means 3% losses. Okay. Due to the temperature is around 25 degrees Celsius, you know, it's due to the ambient temperature is around 0.55 degrees Celsius, so there's a change. You know, KMM is around 2% losses, and the STC is 250. Okay, so we want to do the calculations. So this is the but we have the data here. We have, remember, see, we have the data for the kilowatt hour every month. So that's why we add it here. You know, we add it here. So this is the accurate data. When there is one question about if we have the data, then we can calculate the amount of it. So if we calculate this, so the total number of panels is around 28 panels. Minimum number of panels. Okay. So we in the budget, also in the design, we always look into the budget and the total PV. You know? Okay. So this is also very, very, very important. You know, because we cannot just design a very expensive system. Okay. Okay. For example, here we have a client with a budget of 50,000, invest on a grid-connected PV system to determine the peak array capacity affordable. Okay, and the total number of modules if the cost of similar in the market is around 26,000 for a 4 kilowatt. Okay, using a 250 kilowatt. So this is calculating the thing. So you calculate and then you find the number of panels is around 30 panels that you need to install to get these systems. Okay, and then in terms of sizing, you see this as I say, it's very detailed calculations, which I think maybe I will share this. I will share with you, but this is how you calculate the accurate design. I think I will go back to okay, determining them. Okay, yeah. So this is how we calculate the number of panels in series and parallel, and the minimum voltage and minimum current. This is the balance of system, BOS. Okay, and always, for example, rating the current, in terms of rating the current, is always multiplied by two times, or 30% increase in terms of short circuit current, times the MP, which is the number of panels in parallel, because the short circuit current times the number of panels in parallel. This is for the protection, Okay, like you can see here. So if we have I as 8.15, so it should be multiplied by 2, which is 16 ampere. And then the minimum, which is 1.3 times the short circuit current, which is times the number of panels, which is 2, so 21. So this is the range. Okay. All right. What else? This is also balance of the system. You see, actually, this course we conduct in the fuses here. For example, the sizes of the fuses. The bypass diodes in terms of voltage rating times 2. Short circuit current. So we calculate the fuse, and then what is the maximum and minimum, and then we have examples. Okay, I think. I think this is also one of the topics which in this lecture is the key performance indicators. Okay, how we measure the performance of the indicators of a system, especially I'm talking about the PV systems. Okay, so we always use what we call the yield for the calculations. Okay, so the expected yield, so usually it's equal to the power from the PV array at standard STC conditions, times the number of hours, times the derating factors, times the efficiency of the subsystem. So this is the yield. So if I have 200 watt panels, 200 watt, that is as STC. 200 watt times how many sun hours a day? Maybe 6. So 200 times 6. Okay, times the derating factors, which is due to the mismatch, due to the temperature, due to the dirt, due to the age, due to the shade. Okay, times the efficiency of the subsystem. Subsystem means here we are referring to the efficiency of the cables and the efficiency of the inverter. Okay, so this is actually the yield. Okay, so if we want to calculate the what you call the specific yield, which is the SY, which is actually equal to the expected yield divided by the power from the array. See here, power from the array means actually we don't consider all this number of hours, number of the ratings, and so on. Okay, all right. So, and then also we can calculate what we call the yield, the actual energy meter reading. So it is the yield divided by the PV array. So what is the indicator? If the SY is greater than 1,200 kilowatt per hour, okay, per kilowatt peak per annum, or this is what we call a healthy, okay, annum, or 1,000 kilowatt hour per kilowatt peak per month. So this called system is healthy. Means if you have a system which can give you 1,200 kilowatt hour per kilowatt peak per annum, this or greater than this, the system is very healthy. If it's lower than this, the system is not healthy. This is an indicator. So what does it mean? It means if I have a 1 kilowatt peak PV system, if I have 1 kilowatt peak PV systems, this 1 kilowatt PV system should give me 1,200 kilowatt hour per year. If it give me that, means it is very healthy. If it is not, then that's not enough. That's not healthy. So if it gives 1,200 kilowatt hour, means when you see 1,000, actually we're talking about this is divided by 12. Okay. So if we have 1 kilowatt peak, I'm talking about 1 kilowatt peak system. Okay. If we have one kilowatt, peak system. Okay. This 1 kilowatt should give at least, to be healthy, it should give at least 1,200 watt hour. 1,000 kilowatt hour per year. So per year means when you see per month. So actually, it should give you 100 kilowatt per month. Okay, which is this one. It should give you 100 kilowatt per month. So if, for example, you have 30 days, so then we divide this by 30. Okay, so if 30, if we divide 100 by 30, so we get around 3. It's around 3.3 maybe, you know. So 3 kilowatt hour. You see? So 1 kilowatt PV system should give us at least 3.3 kilowatt hour per day. Then we can consider the system is healthy and is good and is value for money. We call the energy yield of the system. Any questions? I don't know. I maybe stop sharing. Maybe I will stop sharing and then, or maybe I finish this one first. The performance ratio also. There is another indicator. We call it the performance ratio. Okay. So the performance ratio, it's also can be expected. It's around what I call the yield, expected yield over the ideal yield. Okay. Or also we can what I call calculate the actual energy meter reading. Sorry.
No.
Any questions?
I think in the chat box.
Sharing. Keep this card. Any questions? Oh, I think there are quite a number of questions here. Maximum input voltage of inverter was 1 key, but input voltage range is. Oh yeah, this is the maximum. You know, there are two things. You know, this is the operating range, but what happens if you apply 800 or 900? So the inverter will not function, but it will not damage. But if maximum exceed 1,000, it will damage. That's the maximum that can handle. But usually, most of the inverter will have an operating voltage range. Most of the time, between 200 to 600 volt range. Okay, inverter does not work beyond the operating range. Then what is the significant for protection? This is just to it does not work, but it will not damage. Even you apply more than 600, it will not damage the voltage. It will not damage the inverters. Okay, any questions on this? Thing? Anyone have any questions? Because we have already 30 minutes. The second 30 minutes. Okay, because this, as I say, this course actually we require to do a lot of it's hands-on course. We conduct it in 1 week only for this grid connected inverter. To size and calculation, do the calculation, very detailed calculations, and this is what's been used in real cases. All right. So there's no question. Then we can continue. Then we can entire screen number 2, share, then slideshow. Yeah, can you see the screen? Looks good?
Yeah, good.
Thank you. Okay, so another indicator, just now I see the performance. This is the formula for it. And if it is above, 75%, then it is a healthy system. Okay. All right. So this is an example. This is the calculations. How to, and this is how the connections. The circuit diagrams when we connect the inverter. This is the real system. So. For example, here we have an inverter here. This is the inverter, okay? And then, you can see here, you have the PV DC mean switch, okay? And then we have the SPD here. This is SPD, surge protector device here. This is very important. This is for protection, and this here. And then we have another PV switch here, DC, all right? And you can see here, we have a string 1, string 2, string 3, and so on and so forth. You can have a number of strings, and then everyone you must have the SPD, and then we have the DC switch when connect. So, and also if you may have more than one inverter, so you have another inverter here, and then the connections, and then you can connect. So we can see from the other side, then you have AC protection circuits, and then PV circuits, and then the PV. Okay. So, and then you can connect to the PV meters. Okay, and then connect to the grid. Okay, so different requirements, and then even for the cables, for example, what's the minimum type? Must be flexi type, double insulated, and UV resistance. See, the one just now I mentioned, specification for the cable design. Okay. So this is required if, when it is required, so required if the distance between the inverter and the box is more than 10 meters, so this is, you need to have this. The earthing, I mentioned just now, this must be grounded, so earthing, if required, minimum 10 mm. Okay, single core, now for frame PV panels, metal casing, So these are what you call the schematic diagram of single phase grid connected PV systems with single MPPT. So you can have multiple MPPT, but this is the standards what we use. But this is a real what you call circuit diagram that we use. Okay. Yeah, this is more or less the same thing. Here with the multiple MPPT systems, okay. Here the inverter have more than one port. Okay, so in this case, what you can see, the same things here. All the rest, is the same like before, but you can see here you have a few strings, connected to this, and then for another port. And then you have the different. They have also their DC SPD protections. Okay, surge protection device, and then the rest is also the same. So here, because some inverters they may have one port, 2 port, 3 port, whatever. I think I mentioned just now in the specification. Some of them have 3, so we can have 3 connections. Yeah, this is I think with multiple. So if you have multiple, So what you have here, you can see you have n numbers. You can have 3, 4, 5, 6, whatever. And then you have another inverter with a multiple port and so on and so forth. Good. Okay, I think any questions on this part before we move to the next part, which is the control of the inverters. Okay, stop sharing and slideshow. Discard. Okay, any questions?
I think no question.
There is no questions.
Yeah.
Okay, no problem. So we can move to the next one. All right, good. So I think this was in screen number 2. We go back to this one. Yeah, our slides. Yeah. Sharing. Share. Screen number 1. Touch screen. Screen number 1. Share. Okay. And then we come back here. Slideshow. Okay, so you can see the difference between these calculations and the actual calculation. This is a rough estimation, a rough calculations. It's not accurate at all. Okay, but this is just to give you an indication, So if you want only a couple of minutes, then you can do these calculations. Okay, so now I think we go back to the. Sorry. Anyone want to speak?
Nothing.
Can you see the slide?
Yes.
Huh?
Yes, Professor, you can see this slide.
Okay, good. So now we talk about the general control structure of the PV systems. Okay, so this figure actually summarizes the control structures and the different control that we used in these systems. So if you look into this here, so let me take a pen. Okay, use the red one. So we have the PV. Okay, and then we most of the time we use the sensors here, current sensor and the voltage sensor. These actually are useful for MPPT control. Okay, these are important. And then sometimes we have a capacitor here. This is actually to reduce the fluctuations. Okay, in the PV. And then we have a DC to DC converter. This is actually the MPPT. But this is this is a boost optional. Okay, it's optional. Okay, it's a boost, but it's optional. We can directly connect to the inverter. Okay, and then we have after that we have another capacitor. We call it the DC, the capacitor for DC link, for the DC link here. And then we have the inverter, and then we have the filter. Okay, and the transformer. We have the transformer, and then we have the grid. Okay, and then this transformer can be either two or three, means single phase or three phase. And power. Okay, so we inject active power, and also we can absorb and inject reactive power also. And from the grid side, we measure the I grid and the V grid. Okay, so that's the measurements. And this block here summarizes all the control that need to be done with these grid connected PV systems. And then there are in this grid PV systems, there are some basic functions for this grid inverter, grid connected inverters. First one is the grid current control. That is must, because how much current you do. DC voltage control. Okay, DC voltage control here. Grid synchronization. That is the basics and the minimum to have on what do you call from a grid connected. It's a current control, DC bus control, and also because you can see here the VDC, see here VDC, and then we have VDC control here. Sorry, the VDC control. Okay, and then also we have voltage current control. We have grid synchronization. This is the basics one. This is the first layer. Okay, this is the first layer. Basic functions of any grid connected PV systems. Okay, then we have what you call PV specific functions. Okay, so this is the basics for the first one, and then we have the PV basic functions. What? Because we are using PV, so we need MPPT control. We need islanding protection. Islanding, I don't know, anti-islanding protection. Okay, means in case there is a fault on the grid, the inverter should be able to disconnect from the grid. We call the become islanded mode. So this is very important for all the inverters, because sometimes in order for us to protect our PV systems, we need to disconnect from the grid. If there is a fault or there is some, because the grid is too big. Sometimes the fault is the inverter have to connect. And then we have what do you call a PV plant monitoring. Okay, because this is very important. Sometimes the PV plant, so we monitor the irradiance. Is some panels are faulty or whatever, So this is the second layer of control. Okay, and then this one here, you can see we take the inputs from the weather station, and this weather station gives us the irradiance, the ambient temperature, and so on, and that's used to feed into this. All right. Okay, so this is the PV system specific functions and control. So we have a MPPT, we have anti-islanding, we have a PV plant monitoring. Okay, and the last one, which is the auxiliary services, or what we call the supervisory command from the data centers or data distribution office. So we need to have the grid support in terms of V, F, and Q. Okay, so this is very commonly required nowadays, especially for the grid forming inverters. So we need to have the grids. We need to support the grid to stabilize the voltage, the frequency, and the reactive power. Also, voltage fault right through, and also sometimes we may have energy storage systems that have to be part of the system. Okay, and plus, very important, for example, harmonic compensation, because we use inverters, switchings, so there is a lot harmonics in the system. So this is quite important, that to make sure that we compensate for these harmonics. We don't inject, because there is a grid standards, okay, that have to be fulfilled, in order for us to make sure that the system is functioning. Because, for example, there's IEEE standards, and IEEE standards must be the total harmonic distortion must be less than 5%. Okay, and then constant power generation control. So also it can be integrated inside the PV system or inside these grid connected PV systems, where you ensure that there is a constant power, especially during the when it's needed to be supplied to the system. So, and then we have the monitoring and control system. So this is the overall control systems of any grid connected PV system. So I have summarized them in this slide, and I hope it explains almost everything that we expect in grid connected PV systems. I think this is the last slides for this today. So maybe, I don't know how much time we have left. Discard. Yeah, we have another maybe 7 minutes, 6 minutes, 8 minutes for questions. Any maybe we can open for questions. We have another 5 minutes, maybe 6 minutes for questions, if you have any questions. Okay, in the chat box, I think there is no. Yeah. Do we need transformer between filter and grid? Yes, for grid connections, like I said yesterday. Okay. We have 3 types of inverters. We have a transformer, like the one I showed just now, is a 50 hertz transformer. In the diagram just now, it's a 50 hertz. This is what we call low frequency transformer. Okay. We have a high frequency transformers, and then we have transformerless. So this is the options we have. But most of the systems which is in the market, most of them use the low frequency transformers at the moment. Okay. So we need the transformers because you are going to connect to the grid. For example, you want to step up the voltage, to a certain level, or also isolation, because you can see here the isolation. Where is the isolation? It's not there. There is no galvanic isolation in the system. Yes, the filter size. Actually, if we use the filter, if you use the transformers, part of the transformer can be considered as a filter also. So the filter size becomes smaller. Okay. But filters is required to ensure that we filter all the harmonics, especially the low order harmonics. The third, if especially in single phase, third, fifth, seventh, ninth, and so on. If it is like a 3-phase, so we don't have third harmonics, we have only the fifth, the seventh, the 11th, and so on and so forth. So this low order harmonic have to be filtered, and that's the use of the filter there. But the filter size will be relatively small, especially if we use the transformers, because the inductance of the transformers can act as also as a part of the filter. All right. Any other questions?
Professor,
Yes.
yeah, while using the DC-DC converter, you said like optional of the boost converter, right?
Sorry?
Hello. Is I'm audible, Professor?
I cannot hear you. Can you repeat the question?
No, there is an optional converter, right? We can go any other converter, right? DC-DC converter.
Yes. Yes. You can use. Yeah, you can use any other DC-DC converters there. Yeah. It's an optional. It's but that's why I say this. Even you can remove even the DC-DC converter from there.
Okay.
You can remove it. You can directly connect from the PV to the inverter. But you don't have the control on the MPPT. You don't have the control of the voltage, the DC voltage at the outputs, because there is also some trade-offs, of MPPT and the DC bus voltage, because when you operate on MPPT, doesn't mean it gives you the constant voltage, at the DC bus. So these are some trade-offs. Are we going to push the converter to operate at a constant DC or at MPPT? Sometimes So these are some of the issues that actually we face when we have this MPPT and constant DC, at the output voltage.
Okay, thank you.
All right. Any other questions?
Chat box, there is a question. Okay, you have been answered that.
Do we need transformer? I think we have answered this, right? Any other questions? Or even doesn't mean question, maybe comment, or even you have your own opinion, doesn't mean you have to agree, with me, you may have maybe based on your opinions, and I think I forgot to mention about this. All these connections, you have standards. I think India also, you have your own Indian standards. We have the IEC standards. We have IEEE standards. For example, iLending. iLending, we have the IEEE 1574. And we have the VDE 0126 standard. So there is a standard that have to be followed in all the design and the connections of this kind of systems, especially if you are grid connected. When you are grid connected, you need to make sure that actually you comply with the requirements. Okay, very important. There is standards that have to be followed. All right, good.
I think if there is no questions, I think we can close the meeting also, Professor. It is around 11:58.
Yeah. So I think it's good. So I think I will see you on Monday then.
Yes, correct. Monday.
All right. So enjoy your weekend and see you on Monday.
Yeah. Thank you, Professor.
Thank you very much, and bye. Thank you.
Bye.